So in this section we are going to see in details some SPH simulation and this Delta-SPH variant, which Matteo just briefly presented, and some of its application to fluid dynamics problem. So this is the plan of my talk. First of all, I will talk about the why we need and when we need the SPH variants. So is it are they needed in every simulation, or maybe we can just use the standard SPH for most of our application? Then the Delta-SPH scheme and its properties. So I will get into details the details of the how we derive the Delta-SPH scheme and which are the peculiarities of this scheme. Some application of Delta-SPH showing also conversions and validations, and some recent developments and some perspective of this scheme. So just a brief introduction of our background, in order also to let you understand why we focus on this Delta-SPH. Me and Matteo, we come from the INSEN Institute. It's a naval architecture institute. These are the towing tank where we study ship models that are long alpha kilometers. And in this institute, we perform experiments with ships in waves. We still study cavitation of propellers inside cavitation tunnels, sloshing, and the impacts. You can see just a cloud of drops. These are impacts of airplanes against water. So we are really interested in engineering applications. And if we go to the first application of SPH to hydrodynamics, so to flows of interest in the marine engineering, for example, this is the very first one, the one by Monaghan in 1994, where with a bunch of particles, he was able to simulate a dam break against an obstacle, and you can see how realistic is this simulation, even with very few particles. How this describes the flow in a way much better than the finite volume schemes at that time, for example. This is another simulation close to this, appeared in physics of fluids. It's a box falling in water. You can see the recirculation here, the breaking of the wave, and that was quite impressive. That was with a very standard SPH scheme, the one that Matteo explained. And actually now, in a more recent time, we use the same scheme for doing a similar simulation. In our institute, we study also bow waves. These are experiments of bow waves done by Delomont in 2009. And we tried to reproduce this experiment with SPH and with finite volume. This is a good way we think that this is a good way to proceed, trying to compare different numerical scheme and to compare them to experiment to see the different features. And you can see how the SPH can provide more details in the breaking wave of this bow wave with respect also to the finite volume. This is the view from the top. You can see how the SPH can describe better and more finely the evolution of this plunging wave. And you can see also the different scars that the wave produces inside in the flow. These are corresponding to under vertical structures that are generated due to the splashing of this wave. And this was done with the standard SPH. So we were quite happy. And actually, most of the application in the engineering field are done with the standard SPH scheme. Here there is a problem of diffusion of a pollutant in water. Here there is a problem of a dam break. This was the disaster of the Vajont in Italy, and this was there is a landslide here that goes inside the basin, and then the water that overcome the dam, and you can see the evolution of the flow. And this is a tire in the splashing of a tire on water, and a slurry flow in a mineral processing factory. So you can see that SPH has been used for many different engineering applications. But in most of these applications, what we see is distribution of the flow, so particles, and velocities. So generally, these are the two quantities that we look with the standard SPH. What happens when we look to pressure, for example? That is one important quantity that is addressed in engineering. So this is the dam break with the standard SPH, and this is the pressure field. Okay? So you can see that the kinematics is correct, looks correct, but the pressure field is completely noisy. It's completely unusable for engineering purposes. And this is something that as engineers are concerned about, in the sense that we cannot use this kind of pressure field. And actually, the source of this pressure noise is complex, in the sense that has different sources. The first one is due to the nature of the numerical scheme. The fact that it's centered and explicit. I will go into details just in a moment. But the first, let's say that the first source is due to the intrinsic nature of the numerical scheme. The second point is the physical assumption. The fact that in this problem we are weakly compressible, so we have sound speed, we have acoustic waves, and these acoustic waves are produced at each impact, for example, and then they evolve and they disperse, and they are dispersed. And a third element is the Lagrangian character δ-SPH. This is more tricky, and you can see what happens here in this stage of the dam break. We have the particles that follow their Lagrangian trajectory. But at a certain time, following this Lagrangian trajectory, they are arranged on very long stretched lines. And these lines are a source of errors, because the interpolating operators here produce a lot of errors. And so the particles then rearrange on a more uniform distribution. This is done automatically, let's say, in δ-SPH. But every time this happens, we have errors in the pressure field, for example. And we will see this again more in details later. So we have these three sources of numerical noise in the pressure field. And all these three aspects are strictly related, in the sense that whenever we produce, for example, errors here, you can see that these dispersed, let's say, everywhere, and it's the same for the others. They are interacting with each other. Now it's interesting to see just how the different variants address this kind of problems. For example, I put here just three of the most popular variants. The Delta-SPH, the incompressible SPH, and the Riemann-based SPH. So in the incompressible SPH, we don't have any more weakly compressibility. We have an incompressible assumption, and it's not any more explicit. It's a implicit or semi-implicit. In the Riemann SPH, we have Riemann solvers to solve the interaction between particles. So each particle interaction is treated as a Riemann problem. Okay. So we introduce diffusion in each particle-particle interaction. So you can see that the first element, the first aspect, the fact that the SPH scheme has a structure that is centered with like centered differences and is explicit is solved by the Delta-SPH by adding diffusion in the equation, while the incompressible SPH, being semi-implicit, solve this part, and the Riemann SPH solved by introducing diffusion through the Riemann solver. As for the acoustic waves, the Delta-SPH results to be less dispersive, but not very accurate actually, but less dispersive than standard SPH. The incompressible SPH, being incompressible, has not any problem with acoustic waves, and the Riemann SPH is very accurate in simulating the evolution of waves and of shocks, of course, because as the Riemann solvers that accurately calculate the shock propagation. As for the particle distribution, the situation is different. The Delta-SPH keeps the same self-rearrangement mechanism that has the standard SPH, as I showed you before. While the incompressible SPH need a specific technique to rearrange particles, because particles follow the Lagrangian trajectory, and at a certain time the simulation cannot goes on because the particles are too disordered. And for the Riemann SPH, we also need something to deal with it, because when the particles are too disordered, the Riemann SPH introduces a lot of energy dissipation. This is too dissipative. So this is not the whole framework of comparison of these three different variants. There are many other aspects to consider, but it's interesting to see that the three variants try to address these different elements of the numerical noise in the SPH. Okay, so this is the standard SPH scheme, as Matteo showed. So we have the continuity equation with the divergence of velocity, momentum equation. Here there is the artificial viscosity term, evolution of the particle position, and state equation. Here we use a linearized state equation because since density variations are small, we consider that we don't need complex state equations. This is just an approximation around root zero of more complex state equation. Indeed, this is very accurate for hydrodynamic problems. So generally, in finite difference scheme, when you have a centered difference and you are explicit, you are unstable. The scheme is divergent. In SPH, actually, we have centered differences because the particle is here and it calculates the differences with respect to surrounded particles. So, in some way, if you see this in 1D, you can see that we are centered. We have central differences, and we are explicit in time. So we should be unstable, as in the finite difference scheme. But actually, we should agree on what we mean as unstable, in the sense that SPH is never unstable because it's conservative, in the sense that, as Matteo explained, we always conserve the energy. So we are unstable in the sense that, for example, this is, I'll show you directly this simulation. This is a simulation of the dump break without artificial viscosity. So we have no dissipative terms. So we have just the initial mechanical energy, that is potential energy, and then we have kinetic energy and compressible energy. So what we have that this dam collapse, and we have that the pressure field gets more noisy and noisy following the time. So you have that the simulation is somehow unstable in the sense that we have a very high frequency noise, but it never explodes, never crashes. And what is interesting actually is that the errors that we are doing in our scheme goes directly into internal energy. So the scheme is unstable in the sense that all the high frequency that we produce goes into internal energy, but the numerical simulation never crashes. Okay. And so when we add some artificial viscosity, what we have is that the velocity field, which is quite noisy, becomes much more smooth. And this is because we are adding a diffusive term inside the momentum equation, so we are regularizing the velocity field. But for the pressure field, yes, we get something that is better, but not that much. It's not enough. So, as in the standard SPH, we have a diffusive term that represents a Laplacian of the velocity field. In the Delta-SPH scheme, we had a diffusive term here in the continuity equation that represents something like a Laplacian of the density field. Okay, so we are making an analogous. We are adding an analogous term in the continuity equation as in the one in the momentum equation. We are trying, so we are adding a term that has the role to take high frequency energy density field and to move it into lower frequencies. Okay, it's a diffusive term. Let's see, the structure is the same. You can see there is a delta coefficient, like here alpha, then there is H, C0, and then there is this summation on this Psi-j. This Psi-j is this term, and we will look more in details in this. Just to say that this term here is a normalized gradient. So it means that we use we use the arrow. We use the renormalization matrix that was defined firstly by Reynolds and Libesky 2003 to compute these gradients of density, and then we put this inside this term. Okay, it's important to say that this renormalization allows us to evaluate density gradients also when the kernel is truncated. So close to surfaces, close to boundaries, we can, thanks to this renormalization, we can avoid introducing the error of the truncation of the kernel. So why this represents density diffusion? Looking at this, it's not very clear that it's a density diffusion. But we can start from the beginning, from the Morris formula. This is a proposal of formula for the Laplacian of a function. So we have, if we want to evaluate a Laplacian of a function, we can do it by using this expression. Okay, where here we have the difference of the function in j and I, and with these are just differences of the positions. And this formula for the Laplacian of a function was used in 2009 by Molteni and Colagrossi for evaluating the first density diffusion term in the continuity equation. You can see here we replace the f by the density, and you can see that these terms are present in the Delta-SPH. Okay, so we have in our Delta-SPH we have two terms that already come from a density of the density Laplacian. Okay, this was done. This term was the first, together with the one by Ferrari, was the first to propose diffusion in the density field. Then we have also this term. Okay, what is the role of this term? Actually, if we use only the Morris formula, so the Laplacian, the pure Laplacian of the density, it can be shown. It was done by Antonio in 2010. It can be shown that it can be rewritten as a density gradient times the gradient of gamma plus gamma times the Laplacian of the density. So it's not purely when you at a discrete level, it's not purely a Laplacian of density, but it's multiplied by a gamma, so it's close to the boundaries. It's not exactly a Laplacian of density. And moreover, more importantly, there is this term. And this term means that whenever this gradient of gamma that should be 0 inside the fluid is different from 0, we have another source that goes with the gradient of the rho. And so gamma and gradient gamma were already split by Matteo, are the summation of the kernel and summation of the gradient of the kernel. And as Matteo told you, gamma is generally equal to 1 inside the fluid, and gradient of gamma is equal to 0 inside the fluid. But for example, if we are exactly on the free surface, gamma is 1/2, and the gradient of gamma diverges as 1 over h. So it means that this term becomes very large when we increase the resolution. And so this tells us that we will have problem when we are close to boundaries. So the idea is to take this term that will diverge on the free surface and put it back in our diffusive term in order to leave this Laplacian of the density alone. And this is in this way. This is done by adding this term, and I will not show you how this represent this density gradient, but it's an expression of this density gradient times the gradient of gamma. And its shape is done in order to have a symmetric aspect, in order to conserve the whole density field. As you can see, if we use this is the proof of that. If we use the Molteni-Colgrossi term, so the Morris term, Morris formula for the Laplacian of the density, we have this. What happens here? It happens that at the free surface we have the gradient of gamma times the gradient of the density, and these two elements couples and give wrong values of the density. Here, since the gradient of the density goes as the hydrostatic, we have a gradient of the density that is different from zero, and so we have a term that give mass to our particles. Okay, so the particles are getting wrong value of the density due to the truncation of the kernel, while in the delta-SPH, the addition of our renormalized gradients allows to have a good reproduction of the hydrostatic distribution. It is important to say that this kind of phenomenon happens also with the other kinds of filters of the density. There are a lot of works in the literature where they apply MLS correction on the density field or Shepard filters. There are several kinds of filters. All those filters suffer from problems at the free surface. So for long evolution times, you will have distribution of particles like this. So if we compare now our standard SPH scheme with the artificial viscosity to our delta scheme, we have that the velocity field is practically very similar, and this is due to the fact that we are not touching the momentum equation. It's a bit more smooth here, but as for the pressure field, the things are quite different. And this is due to the fact that we add diffusion also in the continuity equation, so that we remove those high frequency that couples with the nonlinearities of our equation that are not removed by the momentum equation, by the diffusion in the momentum equation. Even if here we are adding diffusion in the momentum equation, we are not removing those high frequencies that are created in the continuity equation. And this is done here. More interestingly, if we go towards higher resolutions, we have that the noise that we observe at lower resolution reduces. For example, here we have a much finer resolution. We have 400 particles on the height of the dam break. We have a simulation with the weakly compressible delta-SPH, and it's compared to an incompressible finite volume scheme. Okay, you can see that in this case, even the pressure field is very similar to the incompressible one, and it means this is let's say a clear proof that of the fact that if the weakly compressibility assumption is well posed, in the sense that we are really neglecting the compressible effect, the solution is exactly analogous to the incompressible one. We can the two incompressible solutions are practically the same. This is very important because people say that you are weakly compressible, so you are introducing some unphysical effects. Actually, we are just decomposing acoustic part and incompressible part, and you can see that if the things are done in a correct way, the two solutions are really equivalent. It's important also to say that the advantage of the SPH here is that our numerical computational points are just here, while in the finite volume we have computational points everywhere. The grid is everywhere. Okay, so the computational cost of these two solutions is not the same. As for the implementation of this scheme, it is important to remember that we need a further loop over particle. because we need to evaluate these renormalized gradients. And to do that, we have to calculate the renormalization matrix for each particle. And this means that we need we have to do a loop over the neighboring particles to calculate this, and then use this inside this evaluation. Okay. But if you are using, for example, a higher order integration scheme like the Runge-Kutta fourth order, that is the one that we employ in our institute, we can drastically reduce this cost. And the technique is called the Frozen Diffusion, in the sense that you have this is a scheme of the Runge-Kutta integration. So that at each sub time step of the Runge-Kutta scheme, you need to evaluate the different time derivatives at each time step of the momentum equation, but you can decouple them from the diffusive one. And the diffusive one, so the part related to the delta-SPH, you can calculate it just at the first time step and then keep it fixed during the different sub-steps. So you need to, this is fourth order, so you need 4 different evaluations of the time derivatives, but for the diffusive term, you need just one, just at the beginning. And this means that we are decreasing the accuracy of our diffusive term. We are decreasing the time accuracy time of our diffusive term, but actually we are not interested in accurately integrating it. We are just interested in adding diffusion in our scheme. So this works very nicely, and it allows you to reduce by 50% at least the cost of your calculation. Another thing is that just few words about the properties of this diffusive term. As I said, it's symmetric, so we have that Psi-j is equal to Psi-ji, and that the sum over all the diffusive terms is equal to 0 due to the cancellation of terms, okay? Because those are equals and this is antisymmetric, so sum is 0 all over the domain, so we are not introducing any spurious term inside the global balance of the density. The term is consistent at the free surface, as I showed you, and moreover it vanishes as h goes to 0. So converging, the importance of these terms becomes smaller and smaller because it is multiplied by our smoothing length. Another interesting thing is that we don't need any tuning, in the sense that the range of variation of this delta is very narrow. And actually, for all the simulation that we have been done in the last 10 years, we have always set it to 0.1. Never changed it. And more importantly, this scheme maintains the same energy properties of the standard SPH scheme, in the sense that we can write explicitly the energy components for each term. And I'm going to show you how. In the SPH scheme, we can write a balance of the energy terms. Here we have kinetic energy, potential energy, and compressible energy. And these are the 3 energies of our system. In the standard SPH scheme, without viscosity, these terms doesn't exist, and this is 0. Okay. So in the standard SPH scheme, without viscosity or artificial viscosity, this is constant at discrete level. So you can calculate the kinetic energy as the sum of the kinetic energy of each single particle, and the same you can do with the potential energy, and the same you can do with the compressible energy. That for the linear state equation is simply a function of the density of the particle. Okay? Okay, this is the energy of your system of particles. In the delta-SPH scheme, you have that the time variation of this energy is due to 3 different power terms. Okay, the P delta is the power due to the delta term, is the dissipated energy due to the diffusive term inside the continuity equation. The shape of this expression has been shown in this paper, and it comes out just from writing the energy equation for the system. And this has been shown to be a dissipation of energy because we are adding diffusion. So this has been shown to be a diffused energy, so dissipation of energy. As Matteo told before, P alpha is a viscous power, so it's another dissipation of energy that is due to the artificial viscosity. And here this PS is the power due to the fluid body interaction. And these summation here are done on the solid particle, for example, for ghost particles, let's say. So whenever we have moving solid boundaries, we have energy produced inside our fluid, and it's accounted for through this expression. Anyway, I will not consider solid boundaries for now, so we just focus on these two terms. So in standard SPH, we have only this with the alpha viscosity. In Delta-SPH, we have two power terms. And so we can, if we express our mechanical energy as the sum of kinetic and potential, and we define this Q, this dissipated energy, as the time integration of the power due to the artificial viscosity and the power due to the delta term, to the density diffusion, we can write that the variation of our mechanical energy and compressible energy are due to our dissipated energy. And these two terms are always zero. This has been proven analytically, this has been proven empirically, but these are always zero, and they are always dissipation of energy. So it's interesting to see how this term work inside, for example, a Dambrecht flow. I will show you here the evolution of the internal energy, of the dissipated energy inside the flow. So you can see that for now, the flow remains practically, there is no dissipation of energy because here the flow is practically potential. Then at the impact, you see that some energy is dissipated here, and then bam. Then there is a lot of energy dissipated due to the impacts, and then due to the vorticity, because of the artificial viscous terms. And you see that the flow get more red and red because of dissipation of energy inside our scheme. And we can exactly track where this energy is dissipated and which particles are dissipating energy. And you can see that as the simulation evolves and goes on, the energy is dissipated due to our dissipative terms, diffusion terms, and the flow gets its rest position at the end of the simulation. And here I reported the different components. So in red is the kinetic energy, in blue the potential energy. So trivially you can see that as potential energy decreases, the kinetic energy increases. In green we have the compressible energy, and you can see that it's almost all the time equal to zero, apart from this small peak that corresponds to the closure of the cavity, where we have a strong shock. So we have a sudden increase of compressible energy, and then it decreases as it's a reversible energy. And in black, we have the dissipated energy through diffusive terms. And you can see that it's always increasing, and that it has some very steep parts that are due, for example, to strong impacts, where we dissipate a lot of energy. And here, for example, you can see this is the stage where there are just vortex structures that dissipate energy through artificial viscosity. And in the Delta-SPH scheme, as in the standard SPH scheme, you can calculate the balance of this energy. So if you define an internal energy as the compressible energy plus the dissipated energy, so let's say the diffusive heating, you can compute the balance of the mechanical energy and this internal energy. And their sum has to be constant. So you can check by computing this, so by summing these two energy components, that your total energy remains constant. And if it's true, it means that you are doing a few errors with your time integration. Because in the time integration, you can dissipate energy, you can do errors. So if the errors that we commit in this total energy is large, it means that it's your time integrator that is doing these errors. So this is a way to check also that your integration time step is good, and that you're doing a few errors in the time integration. An interesting thing is the comparison of the mechanical energy between the standard SPH and the Delta-SPH. Because we added the diffusive term in the Delta-SPH, so we suppose it is more diffusive than the standard. And actually it's not. If you see in the red is the standard SPH, in blue the Delta-SPH, and we see that the mechanical energy is dissipated faster in the standard SPH. So even if we in this curve we added a further diffusive term in the continuity equation, we are less dissipative in terms of mechanical energy, because our field, our pressure field is more regular, so we do less error with respect to the standard SPH scheme. Another interesting point is comparing the Delta-SPH and the implicit case, the one that I showed you before, without any artificial viscosity. And here we compare the compressible energy. So you can see that the compressible energy in the Delta-SPH scheme remains always very close to zero, to the rest condition, apart from the peak that I mentioned before. While in the case with the alpha equal to 0, so without any artificial viscosity, any diffusive term, we have that our compressible energy that is supposed to be reversible here behaves as an irreversible energy. So that this all the energy that is taken from mechanical energy goes inside the compressible energy and remains there as a very high numerical noise. It's like a heating, thermal heating. That is the only way the SPH scheme with alpha equal to 0 can dissipate energy. So you can see it goes on increasing this compressible energy. So now I will show you some applications of the Delta-SPH and some conversion test and validation. The first one is the simplest, is an impinging jet against a flat plate with a certain angle of impingement. This is a case where we have an analytical solution for the pressure and for the free surface. And we are really looking to the pressure in this case as a relevant quantity. So this is the coarsest resolution. And this is the standard SPH, that one is the Delta-SPH. You can see that the free surfaces are more or less correctly solved by both solvers. But in the standard SPH, you can see that in the part where the particle have to deviate from the Lagrangian trajectory and they have to rearrange in order to follow this high curvature, we have a lot of noise, and this noise propagates as acoustic waves. While in the Delta-SPH, we have a bit of noise, but the pressure field remains much more regular. And if we increase the resolution, we have that in both cases the noise is less, but still in the standard SPH, in this region, where particles have to rearrange, we still have some noise that is generated. And if we look to the pressure signal in space, for example, measuring the pressure along the plate, here we have in black the analytical solution, in green the Delta-SPH, and in red the standard SPH. You can see that the comparison with the analytical solution is much better with the Delta-SPH. And here we observe measure the pressure in time in a single point, in the point of the peak of the pressure on the plate. And you can see that the noise of the standard SPH is much larger than the Delta-SPH. So it's both in time and space we observe the same thing, obviously. And this is a convergent test. So we increase the particle number inside the width of the jet by keeping the same number of neighbors. So the number of neighbors is always 50 inside the support of the kernel, and we just reduce the size of the particles. Okay, so we are putting more and more particles in our jet, and we can see that for the coarsest resolution, we observe still some noise in the pressure due to the low discretization, but this converges quite rapidly, quite quickly to the analytical solution. Another more challenging test case that is interesting, for example, in the marine context, in the marine engineering context, is the impact of a fluid wedge against a wall. In this case, the things are more tricky because it's an unsteady flow where we have a very high peak of pressure that moves along the wall. I will show you it now. And you need, and actually this pressure bulb increase in time, in the sense that at the beginning it's very small, and then as the simulation goes on, it becomes larger and larger. So at the beginning, we have a lot of difficulties in accurately measuring the pressure peak. And for example, this is the pressure measured on the wall at a certain point on the wall, these are 5 different levels of resolution. So this is a fully converged simulation. And you can see that for the coarsest one, you still have some oscillation due to the fact that the particle have to rearrange in the high curvature zone here close to the intersection between the fluid wedge and the wall. Here the particle have to follow a very high curvature, okay? And in that region the particle have to rearrange, and this causes some oscillation in the pressure signal. But this quickly disappears. Already at the third resolution we have practically a convergent solution. And if we zoom close to the pressure peak, and we compare to an analytical solution from a self-similar solution. So this analytical solution in purple comes from a problem where the wedge is an infinite triangle. Okay, so we have some differences with respect to our truncated wedge, but you can see that this is a zoomed view, and you can see that the comparison is quite good for even for this case. And we applied this, for example, to a real test case, so a real problem, engineering problem. Here, the problem was we are in France, and the context is the EMACOP project. It's a project where we want to study the feasibility of applying wave energy converters in front of existing coastal structures. So here, for example, we are close to the Basque coast. We have a dike, an existing dike, and we want to study the possibility of putting a flap type energy converter in front of this dike. This is a place where we have large tide variations and a very strong sea state, very extreme sea state. So the idea is to try to address which are the extreme loads on these devices, and for this we made several 2D and 3D simulations, changing the tide level, so the level of water at rest, and changing also the distance of this flap energy converter with respect to the wave breaking. So try to see what happens to the loads when the wave break before or after impacting this device. And we will always focus on the pressure and forces on this structure. This is just an example of the evolution of this flow. You can see that the wave impacts with the front that is very close to parallel with respect to the flap, and this has a strong influence to the loads that we measure on it. Here it's well visible. We have this the steepness of this front is very close to it's not parallel, but it's this angle is very small, let's say, between the front and the flap. And so what happens is something similar to the wedge, water wedge impacting the wall. We have a very high pressure peak that moves quickly along the wall. And this can be seen even better in this plane where we have on the x-axis the time, and the y-axis the axis along the plane, along the flap. And you can see that the pressure rise and reaches a very localized peak here. And this is something that is already been observed for waves impacting the walls. And it's a kind of dangerous mechanism for structures, because we have very high and localized pressures that can damage the structure. And you can see here that for other waves we have much smoother behavior of the forces, while for the wave that impacts with the front like this, we have a very high pressure, high force peak measured on the plane. So I will go to the more recent developments. So the thing that we understood in the last year is that Bain Lagrangian is a double-edged sword, in the sense that yes, we like Bain Lagrangian because we can follow interfaces and so on. But look at this picture. This is the picture of Lagrangian trajectories of particle in a finite. This is the solution comes from a finite difference scheme. Okay, so under this solution there is a grid, but then the particles are advected through the velocity, through their velocity, and this would be the particle distribution that we would have in this flow. This is a flow past this S square. If you give this particle distribution to SPH, it will give just errors. So the problem is that if you want to be more accurate, so if you want to really follow the Lagrangian path, you fall down, you have another problem with the particle spatial distribution that will be too disordered for the kernel interpolation, okay, for our convolution of the kernel. And this kind of problem occur every time we try to increase the diffusion. So for example, in this pitch with Riemann solvers, they experience this kind of problem. They have a structure like this that then ends up with a lot of errors when the particles are mixing. Every time we want to increase the accuracy of the operators. So all the different proposals of higher order interpolation will have to address this kind of issue. And every time we want to simulate the high shear flows, okay? So as soon as we try to increase the accuracy, we end up with losing accuracy because of this kind of problem. And actually, the standard SPH and also the Delta-SPH address this problem with the self-rearrangement mechanism. As I showed you before, this is the Lambrecht, and we see that when the distribution becomes too irregular, the SPH try to rearrange particles in a more uniform way. And this is due to the shape of the gradient of the pressure. This is because we have this term here. This is the gradient of the pressure that we want to evaluate. But then we have also this term. And this term, when particles are regular, uniform, is 0, because gradient of gamma is 0 when particles are regular. While where particles are disordered, this term tends, points toward the voids, toward the irregularities. So, and this is also the reason why we use background pressure, because background pressure works with this coefficient that is our background pressure. So that multiplies the gradient of gamma, which allows filling all the different voids, filling all the different irregularities. And this is already present in all the schemes that have this gradient of the pressure, this shape of the gradient of the pressure. Anyway, okay, the standard SPH rearrange have this rearrangement mechanism, so we are happy because we never lose our regular distribution of particles, but we do errors, small errors every time we do this. We rearrange particles. So the idea is to take that gradient of gamma and put it directly on the advection part, in the advection of the position. So whenever we update the position of the particle, we add a small, which has to be small, deviation from it that goes with the gradient of gamma. This is called the particle shifting. It was proposed the first time by Nestor in 2009 and then by Lind in 2012. And for example, this is a simulation done with the Riemann solver, Riemann SPH. This is the dam break in the moment where the jet is plunging. And you can see how many structures you have and then how many errors you do when these structures have to be destroyed. And this is using shifting. So giving a small, because it has to be small, deviation to this position that allows to have always regular particle distribution. And we plugged this also in the Delta-SPH, and we called this new scheme Delta plus SPH. And this allows also to overcome some tensile instability problems. This work was done by Sun et al. In 2016. We performed several test cases. This is the rotating square patch. So it's a square that is rotating. So we have these tentacles that are elongating. And if you perform it with standard or Delta-SPH, you will always experience this tensile instability, because here we have the negative pressure inside. While adding this shifting technique, you can avoid this and recover the analytical solution. These lines are represent the line where these points should move. So it's and then another thing that we added is the tensile instability control. Using the delta plus, we tried to reach higher Reynolds number. This is the flow past an airflow at Reynolds 10,000. You can see the richness of vortical structure that you produce at this Reynolds number. And this is in stall condition, so it means that the flow is completely detached. And so here we would have a lot of a large negative pressure. And as Matteo showed you before, in the standard scheme, in the Delta-SPH scheme, you will have a large void here, due always to that pressure times the gradient of gamma. Here in this paper, it was recently published, we added a small change in the pressure gradient to avoid this and to recover the correct solution. Some perspectives that I will be presented in the next days, just to give you a picture of the different branches and directions that we are following. First, we are trying to plug this shifting technique in a more consistent way, in an arbitrary Eulerian Lagrangian framework. It means that this deviation is purely numerical. It's not just justified in any mathematical way. It's a deviation from the Lagrangian trajectory. In this scheme, in the arbitrarily Lagrangian framework, we try to do this in a consistent way. So to rearrange the equation in order to perform small deviation of the particle position in a consistent way. So avoiding to be inconsistent with the Navier-Stokes equation. Another model is the Lagrangian simulation inside the Delta-SPH. So we tried to see the diffusive terms from a LES perspective in order to use those diffusive coefficients as LES coefficients. So in order to, because actually we showed, we observed that they can be recast in this framework, and if they are variable, they can be used as turbulence model. And then there will be a work by Imada Mani that will, in which will apply the Delta-SPH in multiphase flows. So for air and water flows generally, and many other kind of flows. So these are just some references of these works, of these topics, and that will cover also some of the part of Matteo, and it's all.